Introduction. Welcome back, science enthusiasts, to another exciting episode of our YouTube channel. Dear viewers, hope you have seen Oppenheimer movie, which talks about nuclear energy and the first nuclear bomb made through the same. Let me take you in deep dive of the science behind this. Fasten your seatbelt and let's go to the atomic world together. Understanding the basics. Nuclear reactions are the forces that drive the universe, and they can be divided into two main types: fission and fusion. Both involve the release of energy by altering the nuclei of atoms, but they work in very different ways. Fission, splitting the atom. Fission is like a game of atomic billiards. Imagine a giant atom as a cue ball, and a tiny particle as the 8-ball. When you hit the cue ball with just the right amount of force, usually a neutron, it can break apart the nucleus of the giant atom into smaller fragments. These fragments, along with a couple of neutrons, are released as energy, heat, and radiation. This process is the backbone of nuclear power plants, where controlled fission reactions provide us with electricity. Fusion, the stellar dance. Fusion, on the other hand, is the process that powers the sun and other stars. It's like a cosmic dance party where atoms join together to form a new, heavier nucleus. In this process, hydrogen atoms are combined to form helium, releasing an enormous amount of energy in the form of light and heat. This is the same reaction that occurs in hydrogen bombs, but in stars, it happens naturally. Let's see the key differences. 1. Fuel. Fission. The fuel for fission reactions is usually heavy atomic elements like uranium-235 or plutonium-239. These elements are unstable and can be split to release energy. Fusion. Fusion reactions require light atomic elements like hydrogen isotopes, deuterium and tritium. These isotopes combine under extreme temperature and pressure to release energy. 2. Energy output. Fission. Fission reactions release a significant amount of energy, but they also produce radioactive waste that needs careful management. Fusion. Fusion reactions release even more energy than fission, and the waste produced is less harmful. However, achieving the necessary conditions for fusion on Earth is extremely challenging. 3. Reaction process. Fission. In fission, atoms are split into smaller fragments, and additional neutrons are released, which can trigger a chain reaction. Fusion. Fusion involves the merging of atomic nuclei to form a heavier nucleus, releasing a tremendous amount of energy in the process. 4. Environmental impact. Fission. While it produces energy, fission also generates radioactive waste that needs to be stored safely for thousands of years. Fusion. Fusion doesn't produce long-lived radioactive waste, making it a potentially cleaner and safer energy source. Challenges and potential. Fusion, despite its promise, poses significant technical challenges. Achieving the high temperatures and pressures required to initiate and sustain fusion reactions is a colossal task. Scientists are working on creating magnetic and inertial confinement devices to replicate the extreme conditions necessary for fusion on Earth. The International Thermonuclear Experimental Reactor, ITER, is a prime example of a major international effort to harness fusion for energy production. Conclusion. In the realm of nuclear reactions, fission and fusion are two captivating processes that have shaped our understanding of the universe and the potential for clean, sustainable energy. Fission powers our nuclear reactors, while fusion fuels the stars. Both have their advantages and challenges, and ongoing research aims to unlock the full potential of these incredible forces of nature. We hope you've enjoyed this exploration of fission and fusion. Remember to like, subscribe, and hit that notification bell to stay tuned for more mind-blowing science content. Until next time, keep exploring and expanding your knowledge.